This is what we started with, and we discussed about the central limit theorem and what it talks about, and we discussed about the sample size, when we can use t-test, when we can use z-test, and we understood the concept that sample size is said to be small if n is less than 30, and if it is more than equal to 30, it will consider it to be a sufficiently large to apply z-test. And few more things about the central limit theorem is you can check if with the increase in the n, the sample size, you can see the peakness of the curve is increasing, and with the decrease in n, the curve becomes flat, which we have seen earlier as well in the case of die was tossed 1, the probability distribution was flat, right? Similarly, we can have different distributions. So this is one, the part 1 of the diagram is for the uniform distribution, part 2 is for the exponential distribution, and so on. And in all these cases, you will see that with increase in n, the shape becomes normal, start becoming normal. Normal means bell-shaped curve, right? We have already derived the case for z-score, the calculation of z-score in case of sampling distribution, and we discussed about why it is sigma upon root n, right? Now, to have a more understanding, or the clarity in the understanding, we'll have another example, and you can see on this, we have another example where in order to capitalize, this example says that in order to capitalize on the iced coffee trend, Starbucks offered for a limited time half priced this beverage between 3 p.m. to 5 p.m. right? So Frappuccino is the beverage which is provided between the time period of 3 p.m. to 5 p.m. Now the manager N. Jones at the local Starbucks determined the following from the past historical data. So now we have a past historical data, and this data says that 43% of the iced coffee customers were women. This is one. Then 21% were teenage girls. Customers spent an average of $4.18 on the iced coffee with a standard deviation of 0.84. So this all is the past historical data. 1 month after the marketing period ends, and surveys 50 of her iced coffee customer and finds. So we have a historical data, and now the manager has done a survey on 50 people, and she has data for the sample, and the sample data says that 46% were women, 34% were teenage girls, and they spent an average of $4.26 on the drink. So look at this difference. Here the data says 43% customers were women. In the sample it is 46%. 21% were teenage girls in the past data, 34% was teenage girl, and the average spend were $4.18 from the past data, and 4.26 is the current sample data. Now, N wants to use this survey information to calculate the probability that the customer spends an average of 4.26 or more on the iced coffee. This is one. 46% or more of the iced coffee customers were women, 2, and 34% or more of the iced coffee customers are teenage girls, 3. So these are the 3 questions the manager is trying to answer. And she has 2 data. One is the past historical data, which is a population data, and then another is a sample data. So before we go into the solution part, the first thing is to understand what all is given, what are the given information set, and which method we think is useful in this case, right? So as per our last discussion, what we have discussed in the last 2.5 hours, we have understood that so far we have only read the case where the mean value is given and standard deviation is given, the population mean is given, sample mean is given, but we never talked about some percentage or proportions or something, right? And I mentioned that to apply a right test, we need to have a clear understanding in which case which test is suitable. And we have discussed only one particular case of that method, and that method was z-score. We didn't discuss so far the t-test and the proportion test and so on, right? So in this question, we are going to discuss one more method, which is based on the proportions, right? And how do we identify that this is the case of proportion, that is a case of mean or population mean, and so on? So to differentiate these two cases, understand it this way. So there are cases, or there are situations where the characteristics of the sample doesn't matter to us. What matters to us is only the numbers, the head count. So in this case, the case of Starbucks, what we could see is 46% of women are women. So it doesn't matter if the women are of old age, or they are youngsters, or are in the middle age of 30 to 40 years or so on. They are only interested in if they are women or not, right? And then in the second part, they were only interested in teenage girls, right? So you can define the teenage age means, say, 15 years, lesser than 15 years, or lesser than 18 years, and so on, right? So, or less than 13 years. So in those cases, so if I'm talking about a teenage is defined by a girl which is who is having an age of less than 15 years or 13 years. So if either the girl is of 5 years, 2 years, 8 years, or 9 years, doesn't matter to me. What matters to me is the head count, how many people are there. So when we are only looking for the head count, the numbers, or the frequency, this is the case of proportions. And when the descriptive measures of the data is given, say the mean is given, mode is given, standard deviation is given, that is the case where we apply the z-test, t-test, and so on, the parametric tests, which we are going to discuss. So in the first part of this question, our motive is to determine the question about the probability which the manager is looking for, that the customer spends an average of 4.26 or more, right? So when I'm saying 4.26 or more, that means what? I'm looking for probability of x bar more than equal to 4.26, right? So this is what I'm targeting, probability of x more than equal to 26, and n is what? More than equal to 30. So because n is more than equal to 30, we have a survey of 50 people. So that means by central theorem, we know the data is approximately normal, and so we can apply z-score. And z-score is what? Z-score is nothing but x minus mu upon sigma, this value, standard error. So x bar minus mu divided by standard error. So x bar is known, right? So 4.26 minus mu, population mean was given 4.18 from the past data. 0.84 is what? My standard deviation, and n, the number of people who are surveyed, is what? 50. So by doing that, we got that probability of z more than equal to 0.67. Probability of z more than equal to 0.67, we know how to calculate this. So this is what? Equal to 1 minus the probability from 0 to 0.67. So by doing that, we got the value equal to 25.14% or 0.2514. So from by applying the z-score, we got to know that 25%, or say approximately 25% people will spend more than what? $4.26 on the iced coffee, right? So this is part one. For part 2 and part 3, we will discuss it later on, where we will discuss the proportion part. So I hope this part is clear to all, that when the population mean is given, sample mean is given, population standard deviation is given, we have to apply Z score, right? And I hope at this point of time, at least this part is clear to all of us, right? So moving ahead, a similar example, suppose the foreman of a bottling plant has observed that the amount of soda in each 32-ounce bottle is actually normally distributed, random variable, with a mean of this and standard deviation of 0.3 ounce. If a customer buys one bottle, what is the probability that the bottle will contain more than 32 ounces? So we are looking to calculate probability of X more than 32, where the mean is given and standard deviation is given, right? So to do that, again, we'll go by the same formula. We are looking for probability of X more than 32. We'll convert it to the standard normal variable, and we'll have to find this. Now, to find this, that means we are looking for this region, and this region is what? This region is 0.5 plus the area between this to this, right? So this shows that if I am looking for a single sample, the probability is 75%, right? Now, if we move forward and instead of 1, we are taking 4, then what will happen? So if we take the same question, same example, and do it again, so we can see that the chances are increasing. The question is, what is the interpretation? So what has been changed? Why the probability is increasing? So initially the customer has bought a single bottle. Now he has bought 4 bottles, and the probability is increasing. So why it is increasing? Because we know that with increase in probability, with increase in sample size, the probability of getting that particular thing will increase. And we have discussed it, that with increase in the sample size, the error will be reduced. That is what is happening. So error is reducing. So if error is reducing, that means chances are increasing, right? So this is the interpretation of that. What happens when we are doing a sampling case, when we're increasing the sample size. Now, look at this part. So in case when one bottle was taken, the area was 24.68%, and when we are taking 4 bottles into the consideration, the area is around 91%, right? Similarly, this is a question for your thought, and this is what you should think about and then try to analyze. So I am requesting all of you to please read this and think about. Though means I'll not discuss this in more detail because there are other topics as well. But then the question is, this is a food for thought. So if you are able to understand this part, probably you will be able to relate more to that sampling distribution and why this increasing sample is impacting the score and so on, right? And this gives rise to another concept we are going to discuss, that is called as confidence interval. So this example says that the dean of the School of Business claims that the average salary of the school's graduate 1 year after the graduation is $800 per week. This is the claim of the dean, with a standard deviation of $100. So the dean claims is based upon what? A population, right? The second part is the checking of the claim. So a second year student would like to check whether the claim about the mean is correct or not. So the second year student is kind of challenging the dean's claim. So he did a survey. The second year student did a survey of 25 people who graduated 1 year ago, and determines that their weekly salary is how much? So their weekly salary is $750. So is this consistent with the dean's claim? So if you are able to think about it, this data or the claim or the consistency of the data, then surely you'll get to know that why it is important to have a good sample size. Here the sample size is 25. And what happens when we increase the sample size, right? And this is in line with the same fact what I discussed just before the slide, that with increase in sample size, the probability of falling that in that particular region of acceptance will increase, right? So do think about this part, this example, and try to find the answer if the data is consistent or not, and if it is consistent, how to prove that consistency, because we are going to prove this consistent part or this part with help of another term which is called as confidence interval, right? And mind you, in this case, you are given with the population mean, population standard deviation is given, the sample size is given, the sample mean is also given, so you can always apply the formula what we have derived earlier. So you just have to apply the formula, and then you have to reanalyze, rethink about the interpretation, that if the claim of both the student and the dean are same or in line or not, right? Now
we have to set null hypothesis in this case.
In this case, in the what you call the setting of null and alternate is not required, but yes, in this case you have to go for the confidence interval to see if 25 people are sufficient to claim about the population mean or not, right? And that you can do with the help of the same formula what we have discussed earlier, x bar minus mu divided by the same formula which we did in the sampling distribution case. So we have to apply the same formula here, but this is not a case of what you call hypothesis testing. So we don't have to set a null and alternate hypothesis, but yes, we have to look for the confidence interval, which is a part of hypothesis testing, right?
Okay.
Now going ahead with the same phenomena, we have already discussed the estimator and estimate in case of mean and sampling distribution of mean. So similar to that, which I discussed earlier, there is another part, and this is based upon proportions. So proportions where we are not having the clear picture, we do not have the descriptive measures available. So this is why we have to rely upon the proportion or the percentage of people who are the part of the sample or not. So similar to the terminologies, like say there it was x bar, so here estimator is p bar. So we are going to have a sample proportion from a population, and the notation is p bar. The population parameter is p, and we have to use this estimator to again do the what you call testing of the claims, or say testing of a normal variable or so on. So before we apply the sample proportion, there is some requirement again. So this requirement says that the sample size is sufficiently large, and this can be justified by checking this NP, the product of n sample size, and the probability should be more than equal to 5. So we know that probability of happening and plus non-happening is 1. So P plus Q is what? 1. So we have to prove that NP more than equal to 5 and NQ more than equal to 5. Q is nothing but 1 minus P. So to apply the central limit theorem, or say assume that it is a normally distributed case, we have to check if these two assumptions hold true or not. So if they hold true, then only we can apply. Now I'll show you how similar they are. The formula what we have discussed earlier and the formula for the proportion, they also looks very, very similar, right? So look at this. So if you recall, in case of our central limit theorem, or say the sampling distribution formula, the z-score was x bar minus mu upon standard error, right? And standard error was nothing but sigma upon root n. So we have replaced x bar by p bar, mu by p, and this pq upon root n. Pq upon root n is my standard error. So this formula is exactly looking, it looks like very similar to what we have discussed earlier. The only difference here is it is based upon the proportions. The descriptive measures are not available. So if you recall the Starbucks case where we were talking about 43% women and 46% women in case of sample, so we can answer those questions on the basis of this formula now. So I'll again take you back to the same example where you recall that from the past data, the manager found that 43% were women and 0.21 is the what for the teenage girls. And the number of customers surveyed are 50. And from the sample data, we got that P is equal to 0.46. And for the teenage, it is 0.34. Now, because you can see that N is more than 30, and we can easily check the P into that N is more than equal to 5. So because P into N is more than equal to 5, so we can easily apply the proportion formula. So we applied the same formula in case of proportion to see the case of 46%, more than 46% customers are female. So the chance that more than 46% are female is how much? 33.36%. Right. So by this, we understood the case that there can be different scenarios in which we have to apply different tests. So one test we have discussed is Z test, where we have applied where we assumed that the standard deviation of the population is given and sample size is more than 30. Second case, descriptive measures are missing, not available, and the proportions are given. In that case, we have to apply this formula. And again, we can do the same calculation. Having said that, we understood the two part. One is a case of what you call descriptive measures for sampling distribution, and another is a case of proportionate measures. Now we have to look for the third important area, which I mentioned earlier, that we can also determine the right sample size. So first is sampling, another is determining the right sample. So there are two basic formulas given to determine the sample size even. So the sample size can be determined by these two formulas. In case of quantitative measures, we have to use for this formula. In case of qualitative measures, that means proportion case, we have to use this formula, right? Where Z score, sigma, D is what the error level, and N is what the sample size. So to understand these two formulas, how to apply this formula, look at this. So a study is performed to determine a certain parameter in the community. From a previous study, standard deviation is 46. If a sample error is up to 4, that means D is 4, how many subjects should be included in a study at 99% of confidence interval? So we have to find the value of sample size. So value of Z at 99% is what? 2.58. Sigma is already given 46 square and D was 4. So we applied the formula and we are getting a value approximately equal to 880. So if in a case standard deviation is given, error level is also given, and we know the confidence level. That means what is my tolerance level? Say in case tolerance is what? How much error we can bear. So in this case, the tolerance level is what? 1%. 99% is confidence. So if we know the confidence level, error level, and the standard deviation, we can easily determine what the sample size. So this is one part. This is a case of quantitative study. Similarly, in case of proportionate study or the proportionate study, qualitative study, a problem say that it was desired to estimate the proportion of anemic children in a certain preparatory school. In a similar study at another school, the proportion was 30% detected. So the pi is what? 30%. We have to compute the minimum sample size at the level of 95% for accepting a difference up to 4%, right? So error level is given, 95% confidence is given, and proportion level is given. So we'll apply this formula. Proportion is 30%, 30, 1 minus 30 is 70%, 95%, at 95% of Z score, the value is what? 1.96, and this D is given to be 4%, this is 0.04. So in this case, the sample size should be 504. So these are
Excuse me, sir.
Yes.
So in the case of qualitative, so you don't think that the size of sample is 504 is very large?
504, yeah, 504 is very large, but then it depends on what? Depends on the error level. So look at this. So you are looking for the error of only 0.04. So you increase the error level, surely this 504 will come down.
I think in the case of qualitative, we have to take interview, right?
Yes.
Qualitative
So
estimate.
when we, yes, so look at the case. So if a data is qualitative in nature and you are taking feedback and surveys, so you cannot expect 95% accuracy or 99% accuracy. So in this case, we are looking for 96% accuracy, which is too high, isn't it? So because qualitative studies are mostly we from the literature we know that they bring biases, they bring errors, so we cannot expect a higher level of accuracy. So this is just a certain example where accuracy level is what, 96%. So more is the accuracy, more is the sample size. Lesser is the accuracy, lesser is the sample size. It goes hand in hand.
I think there should be, I think 5 to 10 or maximum 25 or 30 interview is sufficient.
So that is so what you are talking about is the qualitative sampling type, which is based upon snowball sampling, convenience sampling, quota sampling, cluster sampling, and so on.
Okay.
And what I am talking about is a mathematical model or mathematical formula to have a right ideal sample. So this is what ideal sample. If you're looking for a 96% accuracy, you need to have 504 responses. But what you are talking about is it is about the convenience sampling, where we look for the convenience of the researcher and he or she selects say 30 or 40 or 10 or 15 what you call customers feedback, right? But then there we cannot guarantee about the accuracy level.
Okay.
Right. Okay. So if you want to accuracy, if you want to have an accuracy level of 96%, you need to have ideally 504 sample cases. Right. So this is a difference, and many times you'll face this question in a real life setup. That means people will ask the reviewers, or say your interviewer will ask, what is the ideal sample size? So there is a difference between ideal sample size and what we do in actual. So at operational level, obviously we are doing 20, 30 or 40 surveys. But if somebody is asking about ideal sample size, this is how we look at it. Right. So moving ahead, in this I'll give you as a maybe a practice set. These two questions you'll receive as a practice set. So we have discussed so far about the what you call the sampling distribution and the ways of finding the correct sample size, or say the ideal sample size. And if you recall, I left with you with a thought process of confidence interval in another example of Dean's claim, where the average salary was different from the student's claim. So now we have to understand what exactly is the confidence interval. So confidence interval relies upon the tolerance level. So say someone is talking about 5% level of error or 5% level of tolerance. So if I am looking for only to tolerate 5% of error, then that means I'm looking for 95% of right data. So my confidence interval will be 95%, right? So confidence interval is what? It is the range of values which will determine what percentage of value will fall within that range of values. So say if I'm talking about 95% confidence, that means I need to have two data points, and within these two data points, 95% of data points will fall, right? So to find a confidence interval, we need to have a tolerance level defined, right? And now we are going to revise the same set of procedure which we started in the beginning. So if you recall, the step number 1 was to state the null and alternate hypothesis. And null, we understand, it is the claim about the population's parameter. right? And we assume that there is no difference between the sample statistics and the parameter value. That is what is the ideal assumption. And alternate is what? Alternate is the remaining part, right? So there is a certain way of writing the null and alternate hypothesis. So suppose, for example, we are denoting H naught, right? H naught as mu, such that mu has a sign. It is less than equal to, more than equal to. And please remember that null will always have a equal to sign, always, 100% time, right? So null will always have equal to sign. So either it will be less than equal to, or more than equal to, or equal to. And depending on the sign of null, we have to determine the sign of H1, or say the alternate hypothesis. So suppose null is having a sign of less than equal to. So if null is having a sign of less than equal to, then what do you think? So in that case, alternate will be what? Alternate hypothesis will have what?
Greater than.
Greater than. Similarly, if null is having more than equal to sign, then null will have a less than sign. Similarly, if null is having equal to sign, then alternate will be having not equal to sign. So this is very important. This is very important to consider, that which sign will be taken in null, and this will determine the sign of the alternate hypothesis. So suppose null is having a less than equal to or more than equal to sign. In those cases, we say they are one-tailed test. Why one-tailed? Because in case of less than, alternate will be having a right-hand side. So error will fall only in the right-hand side. If null is having more than sign, then error, that means alternate hypothesis will have an error only in the left-hand side. But in the third case, if it is equal to, so alternate hypothesis will have two sign, not equal to. That means what? Either less than or more than. So the sign of alternate hypothesis determine the test. So if it is a one-tailed test, so if it is left or right, if it is a two-tailed test, so what are the two tails, right? So going forward, so if H1, right? So suppose I'm talking about the case of H1, sorry, there is a incorrect sign. So if H1 is not equal to, that means what? Either less than or more than. So if alternate hypothesis is having a not equal to sign, that means it is a two-tailed test, right? And the second step was to determine the error level, or say the chance of the confidence level of the data. So we denote the level of significance by alpha, and alpha is what? Alpha is the risk, or say the tolerance level. So it is the risk decision maker can take of what? Of rejecting a null hypothesis when it is true. So researcher has to determine what is the level of significance he or she has, right? So alpha denotes the what? Risk of rejecting the null hypothesis when it is true. So traditionally, that means in the literature, you will see if alpha is non-determined, we assume it to be 5%, that means 0.05. For consumer research projects, we take alpha equal to 0.01. For quality assurance, say manufacturing part and so, we take alpha is equal to 0.10, right? For quality assurance, we take 0.01, and for the pollings and feedbacks and so on, we take 10%. So this is defined in literature, but yes, it may vary from literature to literature and say books to books as well. So if not given, we by default we take 5%, right? So this is step number 2. Now, after setting the step number 2, that means we know the level of significance. The third part is to determine the critical region or the rejection region. So critical region or rejection region is what? The area of acceptance or area of rejection, and that can be determined only by looking at the tails, right? So everything, the step number 1, 2, 3, they all are interrelated. So look at this. So this is the case of two-tailed. So when I'm saying two-tailed means what? This is a two tail because the null hypothesis is having a equal to sign, right? So here I'm saying that in this case, the null hypothesis H naught, right? This null hypothesis is having this null hypothesis mu is having a equal to sign, right? So if null is having a equal to sign, we know that alternate hypothesis H1, this H1 will have what? Not equal to sign, right? So if it is having a not equal to sign, that means what? So if this is having a not equal to sign, that means error can take place either in the left hand region or right hand region, right? And this is why it is a two-tailed test. Now we know that the total amount of error is how much? The total amount of error is how much? It is alpha. So because total error is alpha and the area under this curve is what? Symmetrical in nature. So this alpha will be also divided into two parts. So it will be divided into alpha by 2 in the left hand side and alpha by 2 in the right hand side. So these two regions are called as region of rejection, or say called as critical region. So out of the whole curve, under the whole curve, we know this area, this blue portion is a region of rejection and remaining region is a acceptance region, or say this 90 to 102 is called as the confidence interval. So these two values, 90 to 102, this is said to be the confidence interval in this case. And beyond 102 and lesser than 90, these are the area where we have to reject the null hypothesis depending on the score we have obtained, right? So now I'll erase this. Take erase all ink. Okay. And look at this, the other case. So the other case is that it is a one-sided hypothesis or one-tailed test. So can anyone tell me, what do you think? What is the sign of null hypothesis in this case? What is the sign of null hypothesis in case of right-tailed test? Anybody?
Sir, less than or equal to, sir?
Yes. So if it is less than, then alternate will have a more than equal to sign. So this is a case of null hypothesis having less than equal to sign, right? Similarly, if we go by this, the next part, so you can easily determine that in this case, the null is having more than equal to sign, right? So in other words, we can understand the tail determines the sign of the alternate hypothesis. So if tail is left, that means alternate hypothesis is having less than sign. That means null is having more than equal to sign. So either way, either forward way or backward way, you can understand the sign of the null and alternate hypothesis. So here we have done two things. Firstly, we have established the null and alternate hypothesis, number one. Second part is the area of acceptance and rejection. Third is the confidence interval, that means the range of values in which we accept or we reject. And this can be done with the help of what? The test. So there are several tests, as I mentioned. These several tests are categorized into two, parametric and non-parametric tests. So what we have discussed so far, that means the Z test, T test, they all are what? They all are called as parametric test because they have some certain parameters. And the cases where there is no parameter involved, they are called as non-parametric. So one example is what? Chi-square. Because in chi-square, we are only bothered about the number of head counts, number of people involved. we do not have any descriptive measures available, right? So we have to apply the, what you call, the parametric test and non-parametric test depending on the situation. And then by obtaining the value, we can decide if we need to accept or reject the null hypothesis, right? So in this part, you can say that there are different measures, or there are different scales of measurement. So there are 4 different scales of measurement, right, depending on how they are described, and they are called as nominal, ordinal, interval, and ratio, right? So parametric tests are more powerful when the data is derived from what? Interval and ratio scales. And non-parametric tests are useful when we are having a data of nominal or ordinal data. Now the question is, what do we understand by the nominal, ordinal, interval, and ratio? So initially we described the data by saying that it is discrete and continuous. Now we are saying that there are different measures of scale, right? And they are categorized into 4 parts. So do we have any clear understanding about what is the meaning of nominal, ordinal, interval, and ratio? Anybody from the meeting who knows about it? What all we understand by these 4 measures of scales of measurement? What is nominal scale? What is ordinal? What is interval? What is ratio? Because this is going to be applied when you'll do a survey, or you'll take a feedback, or you will do a quality check. You need to understand what type of data you are using. Similarly, your software, either you are using SPSS or Minitab or any other software, they will ask you to give the input about the type of data you are using. So you have to describe if the data is nominal, ordinal, interval, and ratio, right? So we need to have a very clear understanding about these 4 parts. So when we say data is nominal in nature, so nominal means what? Nominal means when there is only categorization or labeling of data is done. So say I'm talking about black, red, or any green or sky blue. They are just a label about a color, but they do not compare which color is good, bad, which color is less or high or more or less. So there is no comparison. So when we are just putting a label on a value, on a variable, this is called as nominal variable. But the moment we start trying to compare, so there is a label as well as comparison. So say in a class, or say as a in a company, in an organization, when we start talking from, say, vice president to manager to peon, so there are labels as well as there are comparisons in terms of salary, rankings, and so on, right? So when you compare as well as label, this is a part of ordinal data, where you know which data is less or more. Now the third part, which is called as interval scale, it includes the previous 2. Previous 2 means what? The labeling and the greater than and less than, that means comparison. So labeling and comparison is there, as well as we also can determine by what amount they are different. Say I'm talking about 10, 20, 30, 40. So 10, 20, 30, 40 are what? Are having labels 10, 20, 30, 40. They can be compared. We know 10 is less than 20, 20 is less than 30. And we also have extra information that 10 is less than 20 by 10, 20 is less than 30 by 10. Similarly, 10 is less than 30 by 20. So we know the amount by which a number is lesser than or higher than by the other number. So this is third. And the fourth one is called as the ratio scale. This is the most important scale. So ratio scale is having another added feature, which says that the presence of absolute zero. That means when we say zero has some meaning. Say for example, in case of I'm saying 0 kilogram. So 0 kilogram converted into milligram or gram, or say any other dimension, zero will remain zero. That means 0 kilogram is equal to 0 gram is equal to 0 milligram and so on. But then the same phenomena doesn't hold true in case of temperature. So we cannot say that 0 degrees Celsius temperature is equal to 0 degree Fahrenheit, because there is a change. So in this case of temperature, this absolute zero is missing, right? So in case of height, weight, measurement, you can see that this zero has a meaning. So when you have absolute zero present in the data, it is a ratio scale. When it is absent, it is an interval scale. And the other two we are already well defined. One is called as nominal and ordinal. So now we have already described the scale of measurement. The next part is the fifth step. Fifth step is to compare. Compare what? Compare the value of. So the next part is comparing the calculated value and the tabulated value. So the fifth step is to compare these two values. One is calculated and the other is tabulated. So when I'm saying, yeah, so there is a question from Akankshi that there are a lot of tests, how to choose one of them. So Akankshi, if you recall my discussions so far what we have done, I have categorically mentioned in which case we use proportionate, in which case we use z-test, in which case we can use t-test. So there are certain assumptions we need to remember before we jump into hypothesis testing. So say, for example, if I'm saying n is more than equal to 30 and the population standard deviation is known to us. So if population standard deviation is known and n is more than 30, then in that case, we apply a z-test. So we may have a tree diagram and you can find it easily. It is already available, but then you have to understand. So one is this one, when n is more than 30 and sigma is available. Another case is if sigma is not available, right, and n is less than 30. In that case, you have to apply t-test. Then the third case, when all these descriptive measures, the mean, mode, median, are not given, then we have to go for proportions. So we have discussed a question on that phenomena as well. Then in case of t-test, there are further again bifurcations. So if it is a paired sample or if it is an independent sample. So when we are saying paired sample, that means what? But the both data points are dependent. That means if you are surveying a same sample right now and after 6 months, it is a paired sample. And if you are surveying two different samples at the same point of time, it is what? Independent sample t-test. So this is how we distinguish between the different tests available. Then similarly, we have a chi-square test. So in case of chi-square test, you are given with the frequencies of the data. So we are only having the data with the frequency. That means how many times one is appearing in interval, right? So say from 5 to 10, 10 to 15, 15 to 20, how many people are there in the age group? So in that case, the frequencies are available. So there we can apply chi-square test, right? So, and this chi-square test is utilized to what? To check if there is a relation between the two variables or not, right? The moment this relation is, the comparison is from 2 to 3, we have to move from chi-square to ANOVA. So if it is a more than 2 sample case, it has to go to ANOVA. So ANOVA has also then bifurcations. So this is why I told you that hypothesis testing is not a very small topic which can be understood in a 2-hour lecture or 4-hour lecture or so on. You have to devote a numerous number of lectures or numerous number of hours to understand what phenomena, what assumptions, what has to be, what assumption hold true, so that we can apply this certain test. Then there is also something called as the validity of the test. So we cannot check the validity manually. So this is why the software becomes handy. So we can check the assumptions with the help of the software, and then we can check which assumptions are not holding true, and if it is true, how, right? So this particular session is based only for describing the fundamentals of hypothesis testing. That means you understand the basics of hypothesis testing, how to do that, and which test to apply or how to select the right test or the appropriate test. You need to have further few more sessions, similar sessions, where we can discuss at least one test can be understood maybe in a 2 or 3 lectures like this. So maybe 2 to 4 hour lectures for one single one single test, right? So this is a separate part. So what I'm trying to do, what I started with, is I'm trying to give you the basic gist of hypothesis testing. What are the fundamentals, and then the type of test available and when to apply, how to apply, and then what are the interpretations and what are the nuances of those tests. This has to be understood in a maybe altogether different sessions. So I'm sorry, that means I won't be able to capture all these things together in a single very small session of 2 hours. Because what I recall from my initial discussions and during my master's time, that it may take 44 lectures to understand the type of test available. So it was 44 hours lecture what we did in our master's to understand what all tests are available, what are the nuances of the test, what are the assumptions, how to check all those assumptions through a software, and so on. And here I'm just trying to give you a clear picture of hypothesis testing, what all happens, what is the process of hypothesis testing, right? So once we understand that which test is appropriate for our situation, then we have to compare the values. So one is called as the calculated value, and another is called as tabulated value, right? So the thumb rule says that, so if your calculated value, and please note that if your calculated value is less than the tabulated value, if calculated value is less than the tabulated value, we do not reject the null hypothesis. We do not reject. I'm not saying acceptance. I'll tell you why. Because it is a wrong thing to say that we accept the null hypothesis. So we say we do not reject the null hypothesis. So why I'm not saying we accept the null hypothesis? Because everything what we are trying to claim and research, it is based upon a sample. So it may happen that for a different sample, the results will be different. So it's more like understand the case like the accused who is in the court, and judge is trying to give his judgment. So we say that in the light of the evidence, isn't it? We say in the light of the evidence, we say that the accused is proved guilty or not guilty. That means it is dependent on the evidences. So sample is what? The sample is the evidence. So null is what? Null assume that the person is innocent, and you have to bring some evidences to prove him guilty. And this is why you will see in the law, we say that you cannot say the person is guilty unless it was being proved. It is being proved with the help of the evidences, right? So similarly is the case here. So one thumb rule in this case is, if the calculated value of the test statistic is less than the tabulated value, we do not reject, or otherwise we reject. If it is more than, we reject. So there are 3 ways of accepting or rejecting a null hypothesis, right? There are 3 ways. So number 1, I mentioned, is by comparison of the calculated and the tabulated value. The second we just discussed in the last slide, that was the acceptance region or the rejection region. So if your calculated value is falling in the acceptance region, you do not reject. If it is falling in the critical region, we have to reject. And the third And maybe the most important in these days is called a p-value approach, right? So p-value approach, you cannot miss it is very tedious to find a p-value manually, and this is why we use software for that purpose. So p-value approach again says that if the p-value is less than alpha was what? The significance value. So if p is less than alpha, we reject the null hypothesis. If p is more than alpha, we do not reject the null hypothesis. Now, these are the thumb rules. But to understand what exactly is the p-value, so I'll discuss this part again. So the p-value, look at this. So basically, the p-value, what I'm talking about, is nothing but it is the probability that H naught is true, right? So very small p-value indicate that it is very, the chances of H naught being true is very, very less. So there has to be some cutoff. So the cutoff is what? The alpha. So if p-value is more than alpha, that means we will assume that the H naught is true. And if not, then we have to reject the null hypothesis, right? So the three approaches is, one is a critical value approach, another is the confidence interval approach, third is a p-value approach. Now, because as I mentioned that we are dependent on a sample, right? So it is possible that the researcher who is collecting a data, he may bring biases, or maybe it's more like, suppose you are trying to take a feedback about a soap, right? So if the soap is costly and you are going to talk to a person whose monthly income is, say, less than 5,000 rupees, and the cost of the soap, the daily soap, is, say, 100 rupees per soap. So what do you think? What will be the feedback of these poor fellows? They obviously are not going to like it, right? So sometimes researchers bring biases in the data collection. So this is why it is possible to have different type of error while we are trying to prove or disprove our assumptions. So depending on the nature of the error, we have described it as a type 1 error and type 2 errors, right? And again, it is again a food for thought, that you have to describe which error is a serious error for you, right? So firstly, I'll describe the type of error, and then we'll again discuss with the help of example to understand. So null hypothesis, there are two cases, either it is true or false, right? So do not reject and reject the null hypothesis. So consider this case. So H naught is true, your null hypothesis is true, and you are not rejecting it. So yes, it is a correct decision. But if H naught is true and you are rejecting it, so if null hypothesis is true and you are rejecting it, it is called as type 1 error. It is your alpha. Similarly, if H naught is false, your null hypothesis is false, and you do not reject, yani, if it is false and you are not rejecting, it is type 2 error. If it is true and you are rejecting, it is a type 1 error, right? Now, to understand the consequences of these errors, let's try to understand this with the help of an example, right? So suppose there is a factory which produces crackers, right? So in the case of a factory which is producing crackers, we know that we cannot check the reliability of the crackers by burning each and every cracker, right? Because it is not going to solve the purpose, right? Please suggest some books relating to today's topic. Deepti, though there are many books, but then I personally recommend you to read Levins and Rubens. I can share this to the organization, and surely they'll share with you that which book and which are the which books you can refer to start with, right? So I was talking about the example for the type of errors. So first thing is, suppose there is a factory which produces crackers. So we know that we cannot burn each and every cracker to check the reliability. So how do we check the reliability? So we check the reliability of this by taking one box from a number of boxes as a sample, and then we try to burn the crackers, and we will check if all are burning or not. If all are burning and then there is a sound, appropriate sound coming in, that means it is reliable. Otherwise, it is not reliable. Now, to understand the type of errors, suppose on the basis of the sample of the box you have selected from the sample as a sample, you have taken the lot, because you have to decide. So suppose there are n number of vendors and you are looking for a reliable vendor, so you have to obviously go to the vendor and test one of the samples, right? So you have taken a sample of the box, and on the basis of the sample, means you took a sample, you tried burning all these crackers from the samples, and then you found that they are burning, and then the sound is appropriate, they are perfect. So you place the order. But what happens is, when you place the order and you start getting complaints that the crackers are not of good quality, they are not burning, and then so on. So this is the case. This is the case where you have to define the type of error. So you have taken a sample, right? So remember, H0 is true and you are rejecting, right? That means to understand this type of error, it says that the whole lot of crackers is good, but by mistake you have selected that sample which was of not good quality, right? So when on the basis of that you have rejected the whole lot, this is what your type 1 error. That means you lost the opportunity to have a right sample, right population on the basis of a bad sample. And just reverse of that. That means suppose the vendor has given you, the seller has given you a sample which is of good quality, but he knows it that the whole population, the whole other lot is of bad quality. So on that day of your visit, he has showed you only the good quality of crackers. So on the basis of that, you have selected the sample, right? That means the whole lot is faulty, but then on the basis of the sample, you have selected the whole lot, you have placed the order. So now as a researcher, you have to describe which is a serious concern. Type 1 is a serious concern or type 2 is a serious concern. So I would like to know from you people that what do you think? Which is a serious concern for us? Type 1 error or type 2 error in case of crackers? Okay, so Priyanka is saying type 2, Felix is also saying type 2, Ramya type 2, in case of crackers type 2 is serious. Okay, good. That's very good. So it's good to see that means you all have understood it properly. Yes. So yes, good. So similarly, from case to case, so case to case, the consequences or seriousness will vary, right? So we have described the type of error here. Now going ahead, we understood the consequences and how it is being defined. So let's try to do a small example to understand what we have discussed so far, right? So I have already described p value and the confidence interval and so on. So these are some interpretations. So for the p value, and this we are going to utilize in the example as well, right? So these are the summary, means these are some standard values which is mentioned in the slide. So you can easily recall that for alpha of 10%, the one-tailed test will give you the value of plus minus 1.28. And please remember that why plus minus 1, because the error can be in the left hand side or right hand side. So if for left hand side it is minus, for right hand side it is plus. Similarly, for alpha equal to 10%, for the two-tailed test, it is 1.645. Why? Because the error is divided into two equal parts. So alpha equal to 10 means what? For a two-tailed test, that means alpha is what? 5% in the left, 5% in the right. In case of one-tailed test, the whole error is either is in the left-hand side or either in the right-hand side. So these are some standard values, right, which you have to apply. Now, look at this. So in this example, it says that a packaging device is set to fill detergent powder packets with a mean weight of 3 kg with a standard deviation of 0.21 kg. The weight of the packets can be assumed to be normally distributed. So we are assuming that the weights are normally distributed. The filling the powder, the filling machine is giving you the mean weight of 3 kgs and the error level is 0.21 kg. The weight of the packet is known to drift upwards over a period of time due to the machine fault, which is no tolerable. That means you have an idea that the machine is faulty and it is going to increase the mean weight, right? So suppose the machine, initially the weight of the packets was close to 3, so it is increasing. So it is going to 3.1, 3.2, 3.3, and so on. A sample of 100 packet is taken and weighed. So you have taken a sample of 100 packets and you have weighed all of them. And you found that the mean weight of these 100 packets is coming to be 5.03. So with this data, can we conclude that the mean weight produced by the machine has increased, right? And we have to use a 5% level of significance. That means alpha is what? 5%. So before we solve this question, we need to understand what all is given to us, what all data points are given to us, right? So when we are saying the mean weight of the packets is 3 kg, this is what? My population mean, that is mu. And the standard deviation of the population is what? 0.21. The sample size is what? The sample size is 100. The sample mean is how much? The X bar is 5.03. And how much is alpha? Alpha is 5%. Right? So this is the data points we are known to. Now, remember that we were looking to have a claim. So we are saying that can we conclude that the mean weight produced by the machine has increased, right? So if the mean weight is increased, I think this is not 3. I think this is by default 3. It has to be 5. So sorry for that. This has to be 5, not 3. This has to be 5, right? So we have to formulate the null and alternate hypothesis, right? So what do you think? Because we know that the weight is what? Increasing. So because the weight is increasing, so mu is what? More than equal to 5. This is what? My null. So if null is having more than equal to sign, by default alternate will have a less than sign. And because alternate hypothesis is having a less than sign, that means what? It is a left hand one-tailed test. That means error will be only in the left hand side. And what else is given? So sample size is given, X bar is given. So this is nothing but X bar. So X bar is 5.3, sigma is given, alpha is given. So we know the formula. Z is what? X bar minus mu divided by sigma by root n. So we applied the formula. We got the Z score equal to 1.428. So this is my calculated value. So this is my Z cal. This is Z calculated, right? So Z calculated is this. Now we have to find the tabulated value. So we know that we have to find the value of Z at 5%. So at 5% level, if you recall in the last, this one, remember that at alpha equal to 5%, one tail test value was how much? 1.645, right? So we have to compare this value with help of 1.645. So by comparing this value with 1.645, we see that the calculated value is lesser than the tabulated value. And I mentioned that if the calculated value is lesser than the tabulated value, we cannot reject the null hypothesis. And because we are not rejecting, that means the mean weight of the packets are increasing over the period of time. This is my conclusion, right? So this example shows the steps involved in the hypothesis testing. And obviously you have to practice, say, many questions to understand what, how do we define the null and alternate hypothesis? How do we define the tails? Then how to define the values of z-score? Then what is the right and appropriate test? Then we have to check the assumption of that test. Then after the assumption, you have to apply the appropriate test and then compare. And there are three methodologies available. That is a critical value approach, p-value approach, confidence interval approach. And by any of the approach, you can determine then if the hypothesis has to be accepted or rejected. And finally, on the basis of the acceptance or rejection of the hypothesis, you have to conclude. That means the managerial insight available in the data, right? So this is one part. This is one part where we discussed about the assumptions of hypothesis testing, the steps involved, and the procedure in which we select the right test. And we discussed about three different tests available, where we started from the normal distribution, sampling distribution. Then we discussed about the proportionate tests. And then we mentioned about how do we define the test depending on the sample size, right? So this is the nutshell or summary of the hypothesis testing, right? Or you can say the theoretical understanding of the hypothesis testing, right? So let me know if there is any query you have related to this topic, right? Because we have hardly, and then we can close. So before we wind up or summarize or nutshell, describe this in a nutshell, what we have captured so far. So if you have any query related to this topic, please feel free to raise your hands and then you can ask your query, please. Because I understand it was a content heavy session, and I tried to keep the contents as low as possible, but then this is minimum required to make you understand or to bring you all on the same platform, right? So let me know if you have any query related to any of the topic what we have discussed so far. And what I believe personally, this is my personal belief, that after a session, if you are getting queries from the participant, that means that shows that they have understood. If there is no queries, then there are two possibilities. One, every participant is well aware of the concept. He or she requires no further knowledge. Or the second one, they means you are not, means as a instructor or as a speaker, you are not able to engage your crowd to give them the right meaning.
Sir, thank you for the session. Wonderful learning. Sir, in one slide, you said there was a example like the population where it is the mu is $800 and the sigma is $100, and
Yes.
sample sigma is around 100 divided by square root of 25, which is equal to 20. The sample mean is $750.
Yes.
In that case, can we apply z value as the sample mean minus the population mean upon sigma upon root of n? In that case, will the value be 750 minus 800 upon 20, which is minus 5 by 2, which is equal to z is equal to minus 2.5, and then in the probability of z less than $750 is 0.00621.
Okay.
I just want to know whether the value is correct, sir.
Okay. So I'll tell you this answer in a different way. So if you recall, in that particular example, we discussed that the student collected the data of 25 alumni, and the mean was 750, and the claim of the dean was 800.
Yes, sir.
So in this particular case, instead of looking to apply a z-test or a t-test, it is better to look from the other point of view. This is called as the confidence interval approach, right? So what it does is, when you apply a confidence interval approach, you will be able to find if 800, this dean's claim, this 800 lies within the range of the salary which what the student has calculated. So for example, the student has calculated the mean is what, 750. So obviously in a 1 sigma deviation or 2 sigma deviation, the value will go from 700 to 900, or maybe 710 to 880 or so on, right? So while we formulate a confidence interval, it is easy to see if the null hypothesis value is falling within that value or not. If it is falling within that range, that means it is in the same line. If it is not falling, that means it will not lie within the same range. Now, the second aspect of the same part, you recall that the sample size in that particular part was 25, which was too low, right? So to have a more reliable data, we can always have a sensitivity analysis to check what happens if the sample size goes from 25 to 30 to 45 and so on, and what happens, in which case the confidence interval will include 800, and in which case confidence interval will not include 800, right? So this question can be better understood by applying the confidence interval approach instead of applying the critical value approach. Why? Because here we are looking to have a consistency in the data given by the student and the dean, right? And we are not trying to prove anything with the help of a hypothesis. We are only looking for a consistency of the data, and consistency of the data is can be best evaluated on the basis of the confidence interval, right?
Yes, sir. Yes, sir. Sir, in the graph below, in that problem in the slide, it was written that the probability of z value less than or equal to $750. And the darked portion, that is the critical region, was on the left of the distribution curve, sir. So you are 100% right. I very much understand, sir. So instead of critical value method, we can apply for the confidence interval to compare whether it is near to the dean's claim of 800.
Yes, exactly. So yes, and then in this particular question, you should do a sensitivity analysis by increasing the the sample size, right? So that will give you the better idea.
Fantastic, sir. Thank you very much.
Yeah, thank you. So do we have any other questions? Yeah, so I can see the comments are
comments are very engaging, I think. Thank you for very nice and engaging lecture. Yeah, I think everyone is got the very nice overview of this very important topic. And thank you very much for your time.